Welcome to video number 9 for Physics 102. This video is on a new concept, work. This concept is discussed in section 6.1 of your textbook. Let's begin by trying to motivate why we need a new concept. Aren't Newton's laws enough to solve every problem? Is there some situation under which we cannot apply Newton's laws? Well, no. Scientific laws are applicable everywhere, and Newton's laws falls under this category. So, why do we need a new concept such as work? Let's consider a car on a roller coaster going around a loop-de-loop. Why doesn't this roller coaster car fall off when it reaches the top of the loop? You may think it's because the wheels somehow grab onto the track. And this is not the reason it doesn't fall off. To prove this assertion, I'll show you some videos with a ball going around a track. Since it's just a ball, it can't possibly grab on. Now, if I start the ball too low, it doesn't have enough speed, and it doesn't make it around the loop, and it falls out. However, if I start the ball higher up on the track, it has enough speed to go around the loop. So clearly there is some speed dependence here. If there's not enough speed, then the car won't go around the loop-de-loop and it'll fall off. Thus, there must be some minimum speed that's required for the car to successfully go around the loop. Couldn't we use Newton's laws to solve for this speed? Well, in principle we could, but it would be really hard. To see why, let's think about Newton's laws. Newton's laws help us find acceleration via F equals ma. And we're looking for a minimum speed. The only way we know how to connect acceleration and velocity are through our kinematic equations, such as this one. But we can't apply those kinematic equations here because the acceleration of the car isn't going to be constant. So, thus we need some new techniques and some new methods to solve problems like this. These new methods are work and energy. Work and energy allow us to relate position and velocity without going through time and acceleration as intermediaries as we've been forced to do so far. Work and energy are also useful because they're much more applicable to modern physics like quantum mechanics, which is the basis of chemistry. Work and energy are often easier to use than forces, and by studying work and energy, we will discover a fundamental property of the universe, the law of conservation of energy. So, what is this concept of work? Like many words in science, work has both an everyday definition and a scientific definition. To see the difference between everyday terms and scientific terms, let's look at an example from chemistry. In everyday speech, spontaneous means proceeding from a natural feeling or native tendency, without external constraint. But in chemistry, a spontaneous process is the time evolution of a system which releases free energy and moves to a lower, more thermodynamically stable energy state. Slight difference in the meaning of the word spontaneous between these two definitions. Similar for work. We think about a situation where you press really hard against a wall, but neither you nor the wall go anywhere. In everyday speech, we would say that you're doing a lot of work. But we'll see that under the physics definition, there's actually zero work being done in this situation. So what is the physics definition of work? Work only occurs when a force is applied over some distance. To see what this means, let's consider these two scenarios of a finger pushing a feather causing an acceleration across a table and a strong man holding up a barbell. In the case of the strong man holding up a barbell, he's definitely exerting a force. And colloquially, we would say that he's doing some work. But nothing is moving here. So under the physics definition of work, there is no work being done. However, in the case of pushing a feather across the table with your finger, with some acceleration, the acceleration implies the existence of a force by Newton's second law. Just because we're developing new tools doesn't mean you can forget the old stuff. It's important to understand how these new ideas of work and energy connect to our previous concepts of force. So, from Newton's second law, we know there's a force. The feather is going to cover some distance across the table. So, in the physics definition, there is work being done in this scenario. To explore the physics definition of work a little bit further, let's consider these two cases of blocks sliding across a frictionless table. As they slide, they undergo a displacement, which we will call d. In the top case, the finger is pushing horizontally, parallel to the displacement. In the bottom case, however, the finger is pushing kind of down, at some angle which we'll call theta, relative to the displacement d. The physics definition of work is the component of the force parallel to the displacement multiplied by that displacement, written mathematically as F parallel times d. This quantity is a scalar. It doesn't have a direction. It's just a number. In the top case, the parallel component of the force is the full force of the push. In the bottom case, however, the component of the force parallel to the displacement is this little quantity here at the bottom, which we can see by trigonometry is the force of the push times the cosine of the angle between the push and the displacement. Thus we can write the work in a more useful form as the force applied times the magnitude of the displacement times the cosine of the angle between the force and the displacement. This is the expression for work that will appear on your equation sheet and you'll probably use in most of your problems. So if I wanted to calculate the work for the bottom scenario, I would multiply the force of the push, the displacement of the block, and the cosine of the angle between the push and the displacement. Before we go any further, it's probably instructive to think about the units of work. Work is force times the displacement. The units of force are newtons, and the units of displacement are meters. We know that newtons are kilograms times meters over seconds squared. So, for work, we have kilograms times meters over seconds squared times meters. Or collecting all of our terms, kilograms meters squared over seconds squared. All of these different combinations, which are mathematically equivalent, are known as the joule, which we indicate by the letter J. So now we've got the expression for work, we've got the unit of work, let's talk about the sign of work. Work is a scalar. It doesn't have direction, but it can still be positive or negative. In this case, the component of the force parallel to the displacement is in the same direction as the displacement. The finger's pushing in the same direction the block is moving. So the angle between the force and the displacement is between 0 and 90 degrees, and the work is going to be positive. In this case, however, the force is opposite the direction of the displacement. The angle is now between 90 and 180 degrees, and the work being done is negative. What about in this case, where I'm pushing straight down? In this case, there's no component of the force parallel to the displacement. The angle between the force and the displacement is 90 degrees. And the cosine of 90 degrees is in fact 0. So the finger is doing no work on the box in this case.